Hi everyone, so another video on C2 tools now. So tools is just a weird, I don't know why we use that word to be honest, but um, everything corresponds to triangles, sectors, arc lengths, radians, all this cool stuff which we're going to do a brilliant maths challenge on. Really looking forward to that. Get a bit of problem solving in there with some weird shapes and stuff. So just we're gonna learn these things called the special triangles first, and that will kind of get us practicing our SOHCAHTOA again, but definitely not teaching SOHCAHTOA. We should know that one. So there are two special triangles, and they come in really handy, especially for when you're doing trigonometry stuff. And the idea is you're gonna just be able to know sine 30, sine 60, tan 45, all that kind of stuff without a calculator. So it's just handy to have so you can spot relationships really quickly. So where do they come from? Well, if you do the first one, if you imagine an equilateral triangle with sides 2, you know that the angle is going to be the same in here, 60 degrees, as it's an equilateral triangle. If we then take that triangle and split it into two, so half it, that length then becomes 1, that side length, because this is now gone. And that angle in the triangle here becomes 30 degrees. And like I say, we've got a right angle here. All we need now is that length there. Let's call it x. But through Pythagoras, we know that x squared is the same as the hypotenuse squared. Take away the other length. So that's obviously 4 take 1. Ugh, why have I square rooted? Not yet. So x squared is 2 squared take 1 squared. So that's 3. And therefore x is going to be root 3. Can't be negative because it's a length. So that is your first special triangle. So I absolutely recommend you just draw a triangle. And 2 root 3, 1. Draw another one, 60, 30, 2 root 3, 1. Excuse the writing. Okay, you could just draw them out a couple of times, well, 5 times probably, and then you'll memorize it. Alright? Really handy, because now I can quickly revise my SOHCAHTOA. Let's think about it. What's tan 60 going to be the same as? Well, tan is the opposite over the adjacent, isn't it? So the opposite in this situation, here's my angle of interest. My opposite is root 3, and my adjacent is 1. So root 3 over 1, so tan 60 is root 3. Bang. See, I don't memorize what tan 60 and sine 60 and all that is. I don't need to. I just use my special triangles. Sine 30, what's that the same as? Well, there's 30. Sine is opposite over hypotenuse, so opposite over hypotenuse. So sine 30 is a half. What's cos 60? Well, that's adjacent over hypotenuse. So that's a half as well. Sine 30 and cos 60 are both a half. That makes sense because their graphs are translations of each other. Okay, and we could just keep going with that. We could go, well, what's tan 30 then? Tan 30 is, there's 30. Opposite is 1 over adjacent root 3. You see, comes in really handy. So there you go. And you can work out more of the others. Let's look about the second triangle then. So if we imagine now you have a right angled triangle flat down on its hypotenuse. So this is leaning on a table. Let's say this is an isosceles triangle then with equal sides root 2. So this is 45 degrees, this would be 45 degrees. If this one's 90, that's a right angle, yeah? Same as before, split that into 2. Oh, cool, it's got a bit of a neon light show going here with this green and blue. Anyway, so here's our root 2. And by the way, the whole base length had length 2. Okay, so you've got root 2, and the whole base length was 2. So now we split it in half. This length is now 1. And we can rub this one off now. What's that length? Again, let's call that x. So we know x squared is root 2 squared, so hypotenuse squared, take away the other length. So this is 2 take 1, so this is 1, so x is 1. So we now know our special triangles here. So this is length 1. So again, we can start working stuff out. What's tan 45? Well, remember that's 45 here, but this would be 45 as well, because your right angle was split into 2. Ah, this ball is really doing my head in. Okay, 45 degrees. All right. Tan 45, opposite over adjacent. So 1 over 1 is 1. So tan 45 is 1. That's a common thing that you want to remember. Tan 45 is 1. Cos 45, it's the same as the adjacent over the hypotenuse. So 1 over root 2. Sine 45 is the opposite over hypotenuse. So it's also 1 over root 2. They're both 1 over root 2. You see? Special triangles, done. Learned that? Cool. Now we've got the sine rule and the cosine rule and the area of a triangle. Now you may know the sine rule. You may not know where it comes from, and that might be quite interesting for you. So the proof is for interest. And if you know why things are what they are, then you're more likely to remember them. Okay? So that's why proofs, not only are they interesting, but they're also important. So the sine rule, as you should know, says that sine angle over length, sine beta, sorry, not beta, b. So we're saying capital letters for angles, small letters for sides. So sine of big A over the length A must be the same as sine B over length B, and sine C over C. Why is that though? Can we prove that? Yes, we can. If I split this triangle down, remember these work for any triangles. So you're using the sine and cosine rule for when you don't have 90-degree triangles. Okay, so not having right angle triangles. So if I split this down by the height, and let's call that height h, let's say, you can see I've got 2 right angle triangles here. So let's start thinking of expressions for stuff. So let's look at this c here. So sine of c from SOHCAHTOA, right? Sine is opposite over hypotenuse. So sine c is opposite over hypotenuse. Therefore, a sine c is the same as the height. That's interesting. Let's now work from this side here. So sine of a is the opposite over the hypotenuse. And therefore, c sine a is h, just by timesing up by c. H and h are the same. So therefore, a sine c must be the same as c sine a. And now you can divide through, and there's your first section of the proof. And you can do exactly the same method with your b here. Okay? Exactly the same. That's where the sine rule comes from. Pretty cool, eh? What about the cosine rule? Whoa. Bit trickier this time. Let's do that again. A, B, C. Opposite sides to the angles. So, let's go again. We know that the cosine rule is a squared equals b squared plus c squared minus 2bc cos a. But let's just be clear what we're talking about here. We're saying if we want a side length, the corresponding opposite angle is going to be next to cos. So remember, these are interchangeable, i.e. the formula is also b squared is a squared plus c squared minus 2ac cos b. Or c squared is a squared plus b squared minus 2ba cos c. Do you see? That side is going to match with that angle in there. Let's see where this comes from then. So again, divide this down into 2. This is length h. Right. And also, this whole length, remember, is b. So what if I called that length here x? Let's call that length x. Therefore, this whole length here has to be b minus x, doesn't it? If b is the whole length, then if this one here is x, what's left over must be b take x. And now we can start working with this. So I know it's got to be something to do with cos, because that's what the formula is. So I reckon I'll start there. So cos c, looking at this angle here, cos c is the same as b take x, there's my adjacent, over the hypotenuse, so over a. That might help me in a bit, but let's see. What else do we know? We also know some Pythagoras stuff, don't we, in terms of h. So let's look at that. Let's look at this first triangle here. We know that a squared, the hypotenuse squared, is the same as h squared plus b minus x all squared, don't we? So this thing squared plus this thing squared. And, right, there's one triangle. That's useful. And we've also got this other triangle here. So let's think about that. So this time, hypotenuse c squared is your h squared plus x squared. Right, so we've got some ingredients here. How can we put it all together? Well, let's see. Can we finish this off? I reckon we can. Let's expand this one out. So a squared is h squared plus b squared minus 2bx plus x squared. That's just expanding that thing out there, right? Just make that a bit clearer. Plus b squared minus 2bx plus x squared. We can rearrange this so it contains x, can't we? So if we say that, let's have h squared then is c squared minus x squared. Done. So I've rearranged that to get that. Through substitution, I can put this now in here. So this is a squared equals c squared take x squared, remember that's the same as h squared, plus b squared minus 2bx plus x squared. The x squared and the x squared cancels. So I'm left with a squared is c squared plus b squared minus 2bx. This is very positive. This is good. Because this is starting to look just like the cosine rule I needed up here. The thing is, I need to get rid of that x, but I don't really know what x is. So I did come up with an expression to do with x involving cos c, but I think if it's going to look a bit nasty. It will work, but no. Let's think of another expression for x. What about this triangle here? We know that cos a is the same as the adjacent x over the hypotenuse c. So therefore, x, if you times everything by c, gives you x equals c cos a. This is exactly what we want. So if I shove that in there, I get a squared is c squared plus b squared, subtract 2bc cos a. Done. That's where the cosine rule comes from. Fantastic. Finally, area of a triangle formula. So, do that again. A, B, C, opposite angles, C, A, B. We want the area, and we know the area is the same as half times base times height, don't we? So let's do exactly what we did before. There's the height. That's the height we're looking for, isn't it? So our area, another expression, that's for a right angled triangle, isn't it? This half times base times height, or the area of any triangle, half times base times height. But normally we don't know the height. Normally we only know lengths and angles. So maybe there's another expression for the area of a triangle. Let's think about it. Half times base, so there's our B. That's our base, isn't it? And now we need the height, h. So h, what is h? So at the moment we're on half BH, which is half B, and then let's think about what h is. Well, h, sine C, is the opposite, which is h, over the hypotenuse. And therefore h, if you times that by a, is a sine C. So a sine C. So this is where you get the half AB sine C formula. Half AB sine C. That's your area of a triangle formula. Okay? Fantastic. Now let's just use it a couple of times. Use this stuff. Use what we've just done. So, a couple of examples. When do you need to use this stuff? Well, let's think about it. I'm trying to find this missing value x here. So, I've got an angle and an opposing side, and I've got an angle I want and an opposing side. The sine rule then, I know this is a sine rule problem because I've got alternate pairs facing each other, i.e. sine 20 over 15, because remember sine A over A is the same as sine B over B, same as sine C over C. So sine 20 over 15 must be the same as sine X, the thing I'm missing, over its opposite side, 12. So therefore, timesing up by 12, 12 sine 20 over 15 must be sine X. And if I want to find X, I need to do sine to the minus 1 on my calculator, sine 20 over 15, and I get X is equal to, just make sure your calculator's in degrees, so sine to the minus 1, 12 sine 20 over 15. So this is 15.9 degrees to 3SF. Fantastic, that's good. If I wanted to find the area of this thing, well, I'm going to need to know some other stuff, aren't I? I know that the area is half AB sine C, or the equivalent lengths. So the area, I've got two lengths next to each other is what I need when I'm doing it. So you need two lengths next to each other, and you need an angle to work with. So let's call that C, right? So that's length C. Let's call that angle A. So that's length A. And this angle, let's call that B. Capital B, remember. This board is so screwed up. B. And therefore this side length is B. Okay, so half AB sine C. So if I want to find that, I'm going to have to know what that angle C is. How do I find out what that angle is? Well, remember, in a triangle, they're 180 degrees. So this is going to have to be 180 minus 20 minus the angle I just found, 15.87956, blah, blah, blah. So therefore, my area is half 15 times 12 times sine 180 minus that thing. So 180 minus 20 minus your answer is sine 144.120. So this will give me sine that answer times 12 times 15 times 0.5, 52.7 centimeters squared to 3SF, and that's your area of your triangle. Cool. Let's look at this number 2 then, trying to find the missing distance x. Well, this must be cosine rule. because I've got two sides. I haven't got a pair of known stuff. I don't have a length and a corresponding angle. I don't have that. I don't have any known pair. But I do have an angle sandwiched between two sides that I know. So I'm trying to find x squared. Therefore, as I'm trying to find x squared, it's going to be the other side lengths added to each other, because remember, c squared is a squared plus b squared minus 2ab sine c. So 13 squared plus 5 squared minus 2 lots of 13 times 5. Ugh, epic error. Not ab sine c, ab cos c. It's the cosine rule, you muppet. Cosine. Okay, cool. So 13 squared plus 5 squared minus 2, 13, 5, cos, and then 20 degrees. So x is going to equal the square root of all that stuff. So 13 squared plus 5 squared minus 2 times 13 times 5 times cos 20, and then square root that. 8.48 8.48 centimeters. X equals 8.48 centimeters. 23SF. Okay, cool. I think we could, yeah, we could find the area of that as well. So area is going to equal half. We do have two sides next to each other. That's fantastic. A, B, sine the angle 20. Fantastic. So 0.5 times 13 times 5 times sine 20. Cool. 11.1. Fantastic. Last two then. So what situations are going to we use? This has to be cosine, doesn't it? It has to be, because I've got two sides and um, a missing angle. So, let's think about that one actually. Two sides and a missing angle. So I've got cos. There isn't enough information here. Yeah, there isn't enough information here. I've just checked it, question, and it should be 13. Okay, so this time I'm trying to find the angle x. It's got to be a cosine rule, hasn't it? Because I know three sides. I only have one pair, but it's not a known pair. If you have a known pair, i.e. angle and corresponding side, that's going to be sine rule. Okay, so this has got to be cosine rule, and I'm going to use it to find that missing angle x. So as you know, a squared equals b squared plus c squared minus 2bc cos a. So therefore, 13 squared, the side opposite the angle you're looking for, is going to be 14 squared plus 12 squared minus 2 lots of 14, 12 cos x. So now you need to rearrange to get cos x equals. So bring everything over to the left. So that's that over there, and that gives you minus 2, 14, 12 cos x. But to get cos x by itself, we need to divide by minus 2 times 14 and 12. And therefore, x is going to be cos to the minus 1. That's that. That's 57 over 112, and therefore x equals 59.4 degrees to 3SF. Wicked. And I'll leave you with the last one, but remember you've got a known pair, so you should know what to do. Yeah, you know what to do.